and some physics. So I think today we have to discuss motional EMF. Okay. So it's pretty simple. Suppose you have a rod here. This is a region with a magnetic field. And suppose you are moving this rod with a velocity v. After some time, the rod is here. So this distance here is x. Yeah. So if the rod has moved from here to here, the total flux associated with the rod is equal to B L X. This is equal to flux. So EMF is equal to minus d phi by dt. So it will become minus BL dx by dt. So the dx by dt is velocity. So the EMF is equal to minus BLV. Yeah, so this EMF has come because of the motion of the rod. So this is referred to as motional EMF. Motional EMF is referred to as the EMF induced between the ends of a rod conductor when moved in a magnetic field. So this we have already done. Suppose there is a so this is R. So when you move it this way, suppose the flux is like this. So when you move it this way with the velocity v, negative flux increases. Yeah, negative flux increases. So what happens? The nature of the EMF should be such that it will decrease the flux as per Lenz's law. So I should have a positive flux. So for positive flux means the current should be anti-clockwise. So the current will be this way. EMF is equal to BLV. Current will become equal to BLV by R. Yeah. So now this is equivalent to a current carrying rod placed in a magnetic field. So F is equal to B square L square V by R. So power is equal to B square L square V squared by R. Power is equal to B square L square V squared by R. Power is also equal to I squared R. B square L square V square by R. This power is equal to this power. So mechanical energy is converted into electrical energy. Okay, I will see. Here, motional EMF induced because of the motion of the conductor in a magnetic field. Yeah, is this understood? Then is this understood? Yeah. So if this is understood, so if I have a resistor this side and I have a resistor this side, there is a magnetic field. This is a rod. If you're moving this side with the rod with the velocity v, here on this side, negative flux is increasing. So for positive flux, we will have anti-clockwise current. Here on this side, negative flux is decreasing. So negative flux, clockwise current. This is R1, this is R2. So this moves in this direction. So this current here will be equal to I1, which is equal to BLV by R1. This side, the current is equal to BLV by R2. So work is done on the rod by the external agent. Work is done by the rod on the external agent. I mean, work is done on the rod by the external agent. Then because of that work, current is generated. Then mechanical energy is converted to electrical energy. Mechanical energy is converted to electrical energy. Yeah. Magnetic field is inside. Magnetic field inside is negative. Flux is B into area. So B is the same. As this rod moves, if it comes here, this side area has increased. Negative flux. So negative flux is increasing. If this side area is increasing, this side area is decreasing. So negative flux is decreasing. Just trying to give you reasons as to why the current should go in this direction or in this direction. That's it. Lenz's law, applying Lenz's law. One minute. So we are trying to say that when this magnet goes in or when the magnet comes out, there is a current in the circuit. So these are the magnetic field lines because of a magnet. So as the magnet comes closer, the flux associated with the coil increases. Okay. As a result, there is a induced EMF. Look, this is the north pole. When I bring the north pole this side, look at the voltage. The voltage shifts to the other side. When I bring it out, the voltage is in the opposite direction. Suppose I do the north-south reverse, then the reverse thing happens. Basically, look at the coils, the flux associated with the coils. Now the flux associated with the coils is increasing. Now when it is center, now nothing happens. So even if I change it, nothing is happening. But same thing if I'm here and then I make it change little bit also, there is a change in EMF. Okay, so basically in all these questions, it is the flux which is changing. Because of the changing flux, suppose I move it here, now nothing happens. Now I'm bringing it close. Now I'm bringing it like this. Now nothing happens. But as the magnet comes closer, there is flux associated with this coil is changing. So if you have lesser turns, lesser flux. So you have to bring in fast change for the dial to shift. But here the change will happen more easily. Okay, so this is what is electromagnetic induction. Okay. So yeah. Here. So this side is positive, this side is negative. That is the north pole. EMF is induced. So positives go this side, negatives go this side. We have already discussed this. I told you a conductor is moved perpendicular. North pole comes here, south pole. Positive charges go up, negative charges come down. Then charge is distributed till. If you take a conductor and if you move it in a magnetic field, suppose this is the direction of the magnetic field. positives, when you move it this way with some velocity, positives go up, negatives come down. Now the force on the positive, on the force in this upward direction is QVB. QVB is the force in the upward direction. Now, when the positive is here, negative is here, there's an electric field in this direction. Electric field is equal to, the force due to the electric field is equal to QV by L. So this Q gets cancelled. V is equal to BLV. This V is the voltage. This is the magnetic field. Length. This is velocity. So what you are learning is not new. You are just looking at it from a new perspective. You're just looking at it from a new perspective. Yes, is it understood? Sanjana, why are you bothered about the angle? We are not bothered about the angle between A and B. We are just saying, Faraday just told us one simple thing, that whenever there is a flux associated with the coil is changing, an EMF is induced. So he just said, and that EMF is equal to d phi by dt. So all that I am saying is, if the rod moves from here to here, this distance is x. The flux associated with the rod is BLX. This is area, this is B. Okay. So now d phi by dt with the negative sign. So when I work with it, it works out to be BLV. Now, Lenz told us that the nature of the induced EMF is such that it tends to oppose its cause. So we are just trying to find out where it is. We are not bothered, plus minus, no issues. We just want to understand how to apply Lenz's law and how to apply Faraday's law. This is actually nothing different from chapter number 4. It's actually just a continuation of chapter number 4. Okay. So, do we understand this? So, if we understand this, shall we move on? So, now there are different ways in which the rod can be moved. Okay. Say, for example, the rod can be moved. This is the magnetic field. I can fix this end, and I can move the magnetic, and I can move the rod this way. Okay. So if I'm moving the rod this way, now the rod is here. After some time, the rod comes here. Okay. So the rod comes here, then this is going to be the flux. Yeah. So if this is going to be the flux, this is L. So what is this area equal to? B into full circle is pi r squared. So for 2 pi into theta, this is theta or d theta, d theta. So this is equal to flux. So the EMF induced will be equal to minus d phi by dt. So pi will get cancelled. So it will become B L squared by 2 into d theta by dt. So d theta by dt is what, omega. So the EMF induced will become minus B L squared by 2 into omega. So the EMF induced between its ends will be that much. Now if this is moved in this way, I'll see that the positives are here, negatives are here. Now if it is moved this way, negatives will be here, positive will be here. So this is the EMF induced. Yeah, this is all a part of motional EMF. This question comes very frequently in the board exam. It comes as a 3-mark question. If B is out of the plane, then it will be the reverse of it. That's it. If B is out of the plane, this will be positive, this will be negative. They'll tell you that in the question, they'll tell you that. Mostly they tell inside the plane, so I also do it inside the plane. But if B is outside the plane, it will just be the reverse of it. So if B is outside the plane, this is R. So now suppose this is moved in this direction, then positive flux is increasing. So in this loop, the nature of the current, should be such that it should decrease positive flux. So clockwise current. So it will be a clockwise current. Now we know clockwise current will give rise to a south pole. Remember that loop, clockwise current. Okay. Why are we considering the area between initial and final position as area for area vector? I put d theta, no? It doesn't matter. Wherever you consider, I put d theta. So because I put d theta, it doesn't matter wherever it is. What do you want to consider? So this angle here is d theta. So here d theta. So wherever you take, it is the same thing, no? That nothing is going to change there. So this is one slide. This was the previous slide where EMF is equal to BL squared omega by 2. This was the previous slide where I said with a new perspective, BLV, force is equal to BLV. Yeah, then I hope this is clear. Okay. So if you all have understood this, so whenever we need to discuss the positive flux, the current should be, we need to decrease positive flux, the current should be clockwise. Yes. So now a lot of relatives are there of these questions. So these kinds of questions quite popular in exams. So now I have a rod like this. Now I pivot it at the center. Suppose we have points A, B, and C. This is the magnetic field and it is rotating like this. Question is find VAB, find VAC. Rod of length L is rotated with angular velocity omega. What is VAB equal to and what is VAC equal to? So whenever we need, how can we find that out? Sir, whenever we need clock decrease. And I didn't understand your question, Subiksha. If this rod is moving this way, positive flux is increasing. If this rod is moving this way, the area is decreasing. So area is decreasing, so positive flux is decreasing. So I didn't understand the question. How do you find out? Yeah, this is the rod. So if this rod is moving, then angular velocity omega. Now everything is the same. So for this it will become B L squared omega by 2. Now, but what is L? L will become L by 2. So it will become B, I'll make it L1, B L squared omega by 8, because it will become L by 4. Now, this potential will be equal to this potential. So the potential difference between these two will be 0. So if there are two rods like this, at the ends the potential difference is 0. And the potential difference between this will be BL squared omega by 8, where L is equal to this full length. In all these cases, mechanical energy is getting converted. In all these cases, mechanical energy is getting converted to electrical energy. Okay. Another question which came in the board, they took a series of like this. They put this on a circular frame. And now they rotated it with an angular velocity omega. They called this A, they called this B, and they asked what is VAB. This distance is length. It is rotating with an angular velocity omega. What is VAB? They had actually put 4 like this. So there are 1, 2, 3, 4, 5, 6, 7, 8. They asked what is the potential difference between the center and this point, or center and this point, center and this point. Yeah, I explained to you, Subiksha, if the positive flux is increasing, the current is going to be clockwise. Then I explained to you just now, I explained to you, I hope that was clear. It depends upon the flux. Yeah, okay. Growth and decay of an inductor, we will see. We will do numericals, then we will see. The growth of an inductor we have seen when the current through an inductor, we've seen how the current increases. So that is what is called the growth of an inductor. Now, if you put it off, the current will decrease the same way. So that is inductor, decay. Yes, Videsh, if there is an assignment, you will have to work it out. Okay, so this is the next one. I asked you this one. So understand here, this potential difference is equal to B L squared omega by 2. This potential difference is also equal to the same, also equal to the same, also equal to the same, also equal to the same. So this is equivalent to a parallel connection. parallel connection of cells. So V will be the same, but the current carrying capacity will be higher. Now each of them, suppose you tap between 2 points, now each of them will be able to supply you current. Okay, so yeah, so the potential will continue to remain BL squared omega. The potential difference between these 2 points is BL squared omega by 2. Between this is also BL squared omega by 2, and these are all at the same potential. So when you are taking current out of it, you can take from here and any point on the circumference. So the potential difference will continue to be BL squared omega by 2. So it is equivalent to a parallel connection. It is not a series connection for the potential to increase. So what many people would do is they would say 1, 2, 3, 4, 5, 6, 7, 8. So they will say 8 into BL squared omega by 2. No, that is not the way. Okay, the potential difference continues to be BL squared omega by 2. Yeah, okay, no issues here. So Hayek, I hope we are able to understand. So if you all are able to understand, then let's move on. Now, this is a slightly difficult one. X-axis, Y-axis. There's a magnetic field inside. Okay, sorry. This is a disk. Okay, this is a disk, half a disk. This radius here is R. So now this thing is rotating about its center. It's rotating about its center. So after some time, it would come like this. So they are asking you, angular velocity is omega. They are asking, A, what is the induced EMF between center and end of disk? What is the induced EMF between the center and end of disk? They are asking what is the induced EMF between center and end of disk. Okay, so the way we go ahead with it is this, that again it's going to be the same thing, B R squared omega by 2. See, this is going to be the change in flux, this one. So this is R, so it will become B R squared by 2 into d theta, that is going to be d phi, so by dt. So it is going to be equal to B R squared omega by 2. So that is the EMF induced. But the question was, draw a graph to show change in EMF versus time. That is not change, just EMF versus time. They wanted you to draw a graph. So you have to draw a graph. Yeah. So when you draw the graph, understand now flux is decreasing. So d phi is negative. So minus d phi by dt will be positive. So the flux will be like this. But a stage will come when it is like this. Now when it is going in, d phi will be positive. So now there will be a negative flux. So what will happen is the diagram of EMF versus time here, EMF here will look like this. So it looks like this. So there is a situation of a positive flux and negative flux. Increase in flux and decrease in flux. So assume the magnetic field is this way, out of the plane of paper. So this question was a JEE advanced question. So this is as difficult as a question could get. But again, all that I'm trying to say is it is not difficult. If we understand what the theory is and work with the theory, it is not difficult. So I am saying if the magnetic field is like this, initially the disk is like this. So after some time the disk coming out. So you see this part of it is coming out. Okay, this part is coming out. This part is coming out of the disk, right? So the flux on through the disk is decreasing. So d phi by dt will be equal to minus b L squared d theta. So rate of change of EMF will become negative of that. So it will become B L squared omega by 2. So during the first part of it, the flux will be something. Now it would reach this configuration. Now after this, when it moves like this, now this would be an increase in flux. So the EMF will be minus d phi by dt. So when I do minus d phi by dt, it would come to this. Then next half cycle, it will go this. Next half cycle, it will come this, and it will go on. So this cycle will repeat. Okay. So is this understood? Yeah, graph is like on off in digital medium. Okay. So if you understood this, then here is a question. This is a hanging set of wires with a magnetic field like this. There is a rod here. Okay. So the rod falls freely. Question 1. At any instant of time, if its velocity is v due to gravity, if its velocity is v, find net force acting. Find net force acting on the rod. This is L. Find the net force acting on the rod. Please work on it for a few minutes.
the country to mass.
So the way we go ahead is this, that this is going to fall down. Suppose at some instant of time its velocity is v, there will be an EMF induced here, BLV. Yeah, so there will be a current through this, BLV by R. So that will give rise to a force in the upward direction. So the net force is equal to mg, downward force, minus upward force, BIL. So I is BLV by R into L. So this is going to be the net force acting. That means as it rolls, as it comes down, the velocity will keep increasing. So a stage will come when net force is equal to 0. So after that, the rod will tend to move with a uniform velocity. So that is the equilibrium velocity. So at equilibrium, velocity will become equal to Rmg by b square L square. That is at that point where net force becomes equal to 0. So after that, velocity is constant. Do we understand? Do we get this? Now, a particular year in the JEE Advanced, they ask for what is the velocity. So this m can be written as m dv by dt. Now, if you can integrate this, you will get the velocity. So very clearly, it will be a ln function. Please think about it. As the rod falls, its velocity increases. So the potential difference increases. Potential difference is BLV. So now that potential difference will give rise to a current, BLV by R. So now there is a current carrying conductor placed in a magnetic field. So it will experience a force. So now that force will be against gravity, because gravity is only inducing that EMF. So mg minus that will give me the net force. So that net force is nothing but ma. So that A is nothing but dV by dt. Now I can do some small integration and all beyond around it and ask you different types of questions. This is not required for NCERT board. This is required only for entrance. Okay. So I hope we are able to understand this. How do I know the force will be acting opposite to G? That is what Lenz told. Lenz told the nature of the induced EMF is such that it tends to oppose its cause. So what is the cause of the EMF? The downward fall of the rod. So the nature of the induced EMF should be such that it will be opposing it. So it should be in the upward direction. Okay. Is this clear? Yes. So this is all I have to share today. We will do more questions when we meet on Monday. So we have to just work out more questions and make sure that all of us understand this. So here is the first slide. Here is the second slide. Here is the third slide. So tomorrow we are going to have two talks. One will be from 10 to 11. So 10 to 11 will be done by Pooja, who's a pass out from IISc Bangalore. She was one of our first KVPY students to have joined IISc. So she will talk, and then again from 12:30 we have a alumni from NIT Trichy. He will talk to us. Okay, so please make sure that you are attending. It will be very helpful. This is the fifth one. This is the sixth one. This is the seventh one. Eighth slide. Ninth slide. Tenth slide. Last slide. This question has come many times in the JEE Advanced with different situations. There will be capacitor sometime. A lot of possibilities are there for this question. Yeah. I mean, I can't do much about it. It's up to you. Where are you typing your doubt? Ashwin, put it on Learnity. That will be best. I will be able to see it. Yeah, when we took EMF as BLV, it means that we are considering that there is acceleration. No. When we took EMF, no acceleration. It's instantaneous. It's an instantaneous. So V is changing. I mean, if you're talking about it with respect to the last exam, last option, yeah, it's an instantaneous thing. In the last option, every instant the velocity is changing. So as velocity is changing, EMF changes. So in the last one, if you have to draw a graph, it's a straight line. Actually, even that was a question which was asked in the exam. Draw a graph showing EMF. So it is BLV, but the velocity is increasing. So that is the context where you have to find out what the velocity graph is and then draw the graph. So the velocity will increase. It will go up and then again it will stabilize. Okay. Yeah, we will continue our discussion of this. So don't worry. Next class again we will discuss this. Okay. To be BA. Area is always going to be going to be X. Shouldn't we consider acceleration? We are considering. In flux is only B into area, so it doesn't matter. Suppose in a small time dx, in some small time dt, it moved dx. So dx by dt is the instantaneous velocity, nothing more about it. Okay. Okay, fine. We will discuss. No issues. Yeah. Okay. Bye, guys. Carry on. See you again Monday.